All right, we are actually going to record this as a intro to the main episode, but here we have my trusty co-host, guest host, I guess, Vibhu, as well as Emmanuel from Anthropic. We're going to talk about the circuit tracing stuff and all the interpretability work, but Emmanuel, maybe you want to do a quick self-intro because before we get into it.
Yeah, sure. I'm Emmanuel. I work on the interpretability team here at Anthropic, more specifically on the circuits team. So we recently released a pair of papers about sort of like the work that we've been doing over the last months. And even more recently, we released some code in partnership with the Anthropic Fellows program. It was mostly built by Anthropic Fellows that lets people play with the research, basically. And so happy to talk about that. And we also hope to kind of like keep releasing more things and partner with other groups that are working on similar stuff.
Yeah, amazing. We'll get deeper into like the behind the scenes on the main podcast, but let's maybe just dive right into what you released, because that's the most topical thing. This is like literally you just launched it like yesterday, and we'll probably release this episode in a few days. So yeah, like what can people do, or what do you recommend people try?
Totally. So like at a really high level, the sort of like idea of the research itself is to try to explain sort of like some of the computation that a model did when it predicted a given token. And so in our paper, we kind of like show how to do this. And then we show examples of us doing this on internal private models. And then the release this week sort of lets anyone do it for a set of open source models. So notably, maybe the most easy one here is like Gemma 2B. So you can sort of like think of some prompt and you kind of like can explain any like token that the model samples. And explains here means just like basically blow up the internal state of the model and like show all of this sort of like intermediate things that the model was thinking about before it got to like the final token that it predicted.
Yeah, so some of the things that you guys put out is kind of in the circuit tracing, you have a few core examples, right? So like we can see how these models have internal reasoning states, and there's like multi-hop reasoning. And some of the stuff that we talked about on the podcast was how can people that are interested in how models work kind of do anything, right? So what are open questions? How can people contribute? And it seems like, the follow-up is, okay, it's been a few weeks. Here's a huge library. So, I guess before we even get into it, what are some open questions that you would expect people to like kind of play around with? What are people like going to do? Why should we probe Gemma, Llama? What are interesting things we can do? And any tips on using it?
Yeah, I think there's maybe like 2 to 3 like categories of things that people could do. So I'll go from sort of like the most basic kind of low effort to, hey, if you want to dedicate like a month of your life, you could do that. The sort of like most basic thing is, so it's a Gemma 2 and Llama 1B are like smaller models, but they can still do a bunch of stuff. And so, and for most of the things that they can do, we still kind of like don't really know or have a good mental model of how it is that they do the things that they do. So to give you an example, like one of the things in the paper is this sort of like multi-hop reasoning where, we ask, like Claude 3.5 haiku, like, oh, the capital of the state where Dallas is Austin. It turns out that like Gemma can do this also. And so as part of the release, we have, a notebook where Michael Hanna, one of the Interpretability fellows, kind of like walks through a bunch of examples, including this one. And it's really cool because you can see that actually the way the circuit looks in Gemma, like a really small model, is extremely similar to the way that it looks in like a huge model. Which that in itself is I think like a pretty novel discovery. It's like, oh, you have these models that are like super different. If you look at like their evals or if you just try to use them, they're like just very clearly different. But for this one task, for this one thing, actually, the way that they do this multi-step reasoning is like the same way they actually do the multi-step reasoning. In the notebook, there's both other examples of kind of like fun things that we looked at that I think can sort of spike your interest if you're new to thinking about this stuff. And at the end of the notebook, that's linked in the README, there's like 3 examples of like random sort of like cases that we haven't solved or we haven't labeled that, have like a graph pre-computed for you, and you could just look at it and try to like figure out what's happening. And by figure out what's happening, what we mean is, we might do like a quick demo here, but it's kind of like, look at these representations, try to understand like, okay, like what is the computation the model is doing? And then part of the release also lets you like run experiments to like verify that you're right. So if you think that like, the model like first like thinks about Texas in this case, you can also just like stop it from thinking about Texas and see if like that damages it. And so like the tools to do that are available. And so I would say that's like the first thing is just, I think the hope is there are a lot of behaviors that models do, way more than like any single group has time to explore. And so the hope is like, hey, pick a behavior that you think is interesting and try to understand like what's happening and try to ground it out. And it's like the sort of like baseline thing, and maybe like the thing that I'm most excited about with this release. But then the other thing I do want to mention, to like parts 2 and 3 are just, we also hope that like other groups and kind of like interested researchers can just use this to like extend the method. Like if you have an idea about how to like do this better, the whole code to like make this graph is open source. So you can like take a look at it and just like try to play with it, try to find different ways to like create these graphs and also extend it to other models, right? Like there are many different models. And so, part of making this work on any models, you have to like train the sort of like replacement model, which again, there is code for it and there's other groups working on. And so like, that's also something that if you're excited about, you could say like, okay, cool. Well, I want this to work on like another open model. And you could sort of like add it if you're like, more into sort of like maybe like the engineering and the ML engineering side of things.
Yeah, we actually get into a little bit about how you guys do the extra data viz stuff that makes your blog post pop so much. Should we share the screen a little bit and dive in? I think you guys prep some examples.
Totally. Yeah.
It's just like there's nothing better than the creator of the tool walking through the tool, and we might as well capture that so that people who actually want to do this can follow along.
Yeah, that makes total sense. Let me just like actually share my screen.
My one little experiment, I basically cloned the repo, threw it into Cloud Code, and was like, deal with this. Let's try it end to end. So would recommend, Cloud Code is very good at using this. Basically also, if you're just trying to get started, the circuit tracing tutorial notebook, very good. That kind of goes over all the high level, and then, shout out Cloud Code, try it out. It works very well on this.
That's awesome to hear. Actually, I might just open the notebook first, just like quickly walk through the illustrations. But yeah, you're the second person to tell me that they just had Cloud Code sort of like dig in initially on it. So I'm glad that's working. The tutorial here is like linked at the top of the repo, and maybe we can link it from the podcast, but essentially sort of like walks you through kind of like how to think about graphs. And so it links to these circuits. So here, this is the two-step reasoning that we were talking about. This is kind of like a schematic of it, where it's like the capital state of Dallas, and it's like, it has to think of Texas and Austin. But the notebook links you to all of these circuits here. And this is kind of the thing that you can play with. So this is the UI on, Neuronpedia that hosts this, and that lets you like create any circuit. So here, we could explore the circuit, and if you open the notebook, you could explore it. I'm realizing that I switched tabs. Maybe I'm not showing it. Okay. There we go. Can you see the circuit now? I think so. Okay, cool. But you can make a new graph super easily and quickly. And so maybe this is like the most fun things. When I was playing with right before joining this call is like it turns out that podcast guests are very formulaic. And so if you say like, thanks for having me on the whatever, like Gemma seems to pretty consistently guess that you're like on a podcast, which makes sense, right? Like, why would you say thanks for having me on the blah? And so here we can try to say like, okay, like how does Gemma know to like complete the sentence with thanks for having me on the Latent Space podcast? And so here, the way you generate a graph, right, is you type a sentence where the next word is the thing that you're interested in. And then you kind of try to explain like how the model got to the next word. So here you can give it a name, and then you can mostly just not worry about any of these parameters, I think, if you're just playing with it. And you can click Start Generation.
And what this generates, like something important for people to know is that these are trained on base models, right? So they're not chat models. So basically when you train these models, they're just trained to predict next token, and they don't have that user assistant chatbot flow. So they're prompted in a way such that, the output should basically just be the next word.
Yeah, you kind of want to think about it as like maybe the prompt or the text you're getting is like the text of like a book or an article rather than a conversation, where it's like, what is a sentence where if you were to read it in a book, like the next word would be sort of like the interesting one. Yeah. You can click on it. Sort of like takes a little bit of time to load because there's just a bunch of data. So what we're going to show you here is basically like almost every single feature that activates in the model. The features are these intermediate representations. And at the bottom, there's the prompt. So here it's like, thanks for having me on the Latent Space. And at the top, you can see like what the model sort of like output. So it's most likely output is it's pretty confident that we're talking about a podcast. And, it has like some random stop tokens, blog, show, and then some stuff that I think like makes less sense, but also like these are small models. And so sometimes they say random stuff. And so like the way that you could then explore this would be like, okay, so the model says podcast. So like, why does it say podcast? So you can click on this output and say like, what are the features, again, these like intermediate representations that have an input to this. So it seems like there's features at here. This is the layer, like layer 18, that already like are about podcast episodes. You can know this because the features have a label, but also if you want, you can look at the feature itself here. And here you can see that like this shows you like other text that the feature is active over, and it's just like text about podcasts. So that's like a way that you can also like understand what the features are. And then you can keep going back. So it's like, oh, okay, so it said podcast here because of this podcast feature. Where did that come from? And it's like, oh, it comes from like words related to podcasts, words associated with podcasts, as well as like an interview feature. And also just the word on. So there's like a bias. Like if you're saying like blah, 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 having it on, that sort of like slightly increases the chance that you're talking about a podcast at all. And you can sort of like keep going back, and kind of like explore the graph interactively. I would say that like the way to do it, and we talked about this on the like kind of like longer version of the podcast, but it's like, you know, kind of like chasing from the interesting outputs back or from the interesting input forward. There are many nodes on these. I like wouldn't recommend looking at all of them. You can also sort of like prune them a little more aggressively here if this is too busy, and kind of look, this shows you like only the most important ones, and you can sort of like be pretty extreme with it if you want. Or you can show the whole thing and then be like super overwhelmed. Once you kind of do this, you can then kind of like group your nodes into similar ones to kind of like make a graph. I actually made this little summary earlier, so I can just share that tab. So this is the exact same graph, but just before hopping on, I kind of like did a few groups. So this is like same thing, podcast. It's like, oh, there's like a bunch of those that are like podcast episodes. There's a bunch of things like discussing podcast. There's a note about expressing gratitude that amplifies that you're like on an interview or a podcast. So like one fun experiment you could do here, right, is like, oh, like what happens if I mess with this? Like if I don't, like if I mess with the like, oh, this person is like grateful to be on, and just is like, this person is on, does it think you're on something else? Like maybe there are things that, you know, you could be on that you're not grateful for, like, oh, you're having me on trial or something. I don't know. Like that could be one interesting sort of like experiment to see what the causal effect of this is. And again, you could sort of like label it more and explore it more. And this UI, the whole point is for it to be like snappy and quick. So you can just like generate a bunch of graphs pretty easily, right? Like maybe this wasn't exactly what you wanted. So you're like, I'm super unhappy to be on the latent space. And then you can see what it completes for that or whatever. And you can sort of like just continuously play with it and get a better sense for your hypotheses. Oftentimes you kind of like want different prompts, you know, different examples that are similar to kind of get a sense for it. And then if you're really curious and you want to dig in more, that's when I would recommend going back to like the code base and some of the notebooks. Maybe one last thing I'll say on that is that the notebooks themselves, they can all be run in Google Colab, and all of the code, as far as we can tell, we've like tested all the notebooks, just like runs on Colab. And so that means that like you don't need, on the free tier, to be clear, like you don't need like an expensive GPU. You can just run this and kind of like run your interventions and play with it. And so in this notebook in particular, the intro one, we show you how to do these interventions. And here we're like, what happens if we turn this node off? And what happens if we turn that one off? And what happens if we turn this one off? And what happens if, you know, we inject one from one prompt into another one? And so I think that's the sort of like deeper dive, trying to understand the mechanism better. But if you're just trying to even like get a sense at all of like, how does the model do X? You can just generate a graph and take a look at it.
Incredible.
Very cool.
Is there, when I look at the graph, there's a thought in my mind about maybe this is too easy, too perfect. And one version of this is there's supposed to be superposition, and here there's no superposition, kind of.
Well, there is superposition, and like we're sort of like, so maybe I can share the like graph again and like answer your question, which I think is like, what are we hiding here? Where are the skeletons?
Yeah, this is like it's too clean. I'm like,
so
yeah.
So okay, so maybe like a good example is, and we're gonna like make this slightly less overwhelming here, is like, okay, so you look at this graph and you say like, yeah, like we don't actually understand how models work fully. So like, what are you hiding here? And the thing that's like important to know here is, you know, I didn't say this explicitly, but like the layers are like arranged here. And so let's just look at like one layer. So for this layer, what we're saying is like the only thing that is happening or that's like important enough is this one feature, which is just like one small direction in the model space, right? Like one dimension we've pulled out of superposition, or let's say that for now. But then also there's these diamonds, and these diamonds are errors. We talked about them on the longer podcast, but they're just like when you train these replacement models to replace some of the model computation, you successfully replace some of it, and then some of it you fail to replace. And so this is like everything that we don't understand. And so that means that like sometimes if you look at an input, like this guy's input, you'll see a bunch of errors here as the input. And so essentially, there's some graphs and some examples where like if most of the stuff that you see is these errors, basically that just means like, hey, for this prompt, we were not able to sort of like explain, that part of the computation. And so at least that part is like an explicit sort of like we show it in your face where it's like, here's what we don't understand. And so you can sort of like see what we don't understand. There's also, I will say like one more thing. There's like a bunch more stuff that can get you. And that's like in the paper, but like one example here that I'll just say is like, these are just MLPs. So the model has both attention heads and multilayer perceptrons, MLPs. We don't just do it. Like we completely ignore attention, or like we don't try to decompose it at all. So there's some prompts where like all of the interesting stuff is attention. And here you're just not seeing it at all. The way that it's materialized is like you have an edge from here to here, and like some attention head did a bunch of stuff. You don't know what it is. And so that's also the part that we're sort of like not explaining. So there's definitely, I don't want to make the claim that we explain everything. I think the correct way to think about this is like, if you look at a prompt and you can, by tracing through these, not hit any errors, hit nodes that make sense, and build up a reasonable hypothesis. And then when you test it with interventions, it works. You've at least understood some, and presumably like a reasonable proportion of the computation. If your interventions are working, that means that it's like the thing you found is not just like a side thing. It's part of the main thing that the model is doing. And so, then the question is like, how often does that happen versus how often you just hit these errors or you're like confused? And I think that's just sort of like what works and what doesn't summary here.
Crazy. I mean, congrats on this work. I know you're low on sleep because you worked really hard on shipping it and you're a perfectionist. I just think like, yeah.
Sorry, I'll just say that like the actual brunt of the work here is like the Anthropic fellows. Yeah. They, I mostly just like coordinated things left and right, but they sort of like did all of the implementation as well as, folks on the like Neuronpedia decode research side also did, the lion's share of the work here to actually have the front end UI.
I'll just say like, Vibhu and I were at the Good Fire meetup yesterday, where there were a lot of interpretability folks. I was shocked at honestly how young most interpretability people and work are. And this is a very young field, exactly like you say in the podcast. There's a lot of fresh green grass here to tread. And it's just really inspiring. Vibhu, do you have any other like final thoughts or comments?
Yeah, no, I think there's just a lot of open work to be done, and we talk about this in the podcast too. And just to reiterate, like how good the tooling that you guys put out is, like even the fact that, without diving into any code, you can enter in a prompt and start to play through these circuits in like minutes. It's pretty incredible. Like I could share another one actually. So I was doing this with Pomsky and I finally got it to work. So our guest host of the episode is Mochi, my little dog. She's our distilled husky. So she's on the podcast later. And, I basically put in like, I had to guide it quite a bit, but my prompt is a Pomsky is a small dog that's a breed of a husky and then, I'm expecting it to put out Pomeranian or Pom. Let me share my screen real quick. And then we can kind of dig through. This is me like,
by the way, her tagline, while you put it up, her tagline is officially Mochi the Interpretability Husky.
Today.
For today. Yes. We're going to change our tagline every episode, but yeah.
It feels a little weird, we're digging deep into what Mochi is. But basically, this is me, like, no background, like 2 minutes in, just put in a phrase, and now I get to play around with features, right? So this is also called Please with 4 S's because, I tried a few prompts. It's okay. We struggle. It only took a few minutes though. So, Pomsky is a small dog breed that's a mix of a husky and and then the most probable outputs, now it says Pom. So, okay, let's dig into what some of these are. I'm basically just going like fresh, haven't done this before, but words related to animals, their emotions, their health. We have a feature for dog, golden lab, mentioned dog breeds, especially high maintenance. This is basically like AGI. It knows Pomskys are high maintenance. It's figured it out. But realistically, as I dig through these features, I can start to pin them, layer them through. Mentions of garbage and waste. No, that's not nice. But basically,
interesting.
And this is already me pruning out most of the features. As I open it up, it talks about different things like dog breeding. What else? Related to animal welfare. So and then you can dig through all this. There's just so many things that this is in a matter of minutes. I basically made a graph, put in a sentence, and now I have an output and I can traverse through what are different things. Okay. Animal science, right? So this breed is relatively new. It's not that common that big huskies and little Pomeranians naturally have offspring, but let's dig through animal science versions of this. And then we have interesting little features. So it's very easy for people to kind of get a different understanding of what goes on throughout layers in models, but that's just my fun little experiment of getting it to work.
Oh yeah. And I think one thing that I would do if you were curious, or maybe I'm just going to try to bait some listeners into doing it, is you could be okay, let's try to trace why it said Pomeranian here. And maybe there's some of it is about dog breeds, and some of it is about specific characteristics of a husky. And then you can ask the same question, but instead of husky, you try some other dog breed, and then try to see if you can if you understood the circuit well, and if you identified where it's thinking about huskies or where it's thinking about breeding two different breeds, then you should be able to swap these in and out and get it to say whatever you want. And if you didn't, then maybe there's something complicated going on. But yeah, very cool that you got this going on so quick. That's the whole goal. That's super exciting.
Yeah. And no disclosure. This was 5 minutes of just playing around, and there's stuff to learn there, right? Okay, what happens with dog breeding? What are traits of these dogs? And then, the next step for me would basically be, let's try clamping some of these features up or down. Let's do different breeds and see if it makes sense, right? So if I have husky traits and a different mix, and then, can I get out what's going on? But it also shows internally that there's more than just token completion of, this plus this equals this. No, it has some understanding of characteristics, right? This is a pretty stubborn dog. It has a stubborn feature pretty high up that activates. So very, very cool stuff. I think it'll be cool when we apply this to more serious topics. Right now, when it comes to LM evals, right? We have pretty straightforward evals, right? How good does it do on math? Can it write code? Does stuff compile? But we don't have vibes-based heuristic evals, right? So does it understand different queries should be concise? Should they be verbose? Can we kind of trace through how it gives responses to this stuff? And then the other part is, as we go past base models, how does this happen for different phases of models, right? So if I have a base Gemma and I have a chat model, what are differences in their attributions, right? What happens kind of in that diff of training? So that's kind of one of my little interests in Mech Interp. What happens as we do more training? What are we really changing?
Totally. Yeah. You can think about sort of comparing different models. And for me, different models is either Gemma versus some other model, or early Gemma versus late Gemma in pre-training, or fine-tuned versus not fine-tuned. I think there's also a sense in which somebody yesterday was telling me oh, it's fun. I've been playing with it on the sort of weird riddles that the models get wrong. You're not limited to studying what the model can do, right? If the model's failing at something counting the number of letters in strawberry or whatever, you could just try that and try to figure out the circuit for well, it's getting this wrong. Why? Maybe you can see in its representation that it's thinking about something obviously incorrect, right? And so I think that's also a fun thing to play with.
I think that's it for our little intro chat and coverage of the open sourcing. Let's dive right into the episode next. But Emmanuel, your amazing work, and I'm so inspired. And also just I think this puts a human face on the interpretability work. I think it's very important, and we'd love to keep doing this, whatever you got next coming up.
Well, yeah, thanks for having me. Again, I should say, cool to put a face on it, but definitely want to call out this is a huge team of people with me. I'm just a talking head here.
And paper lead, you did the work, but take credit.
I think that happy to talk about more Interp things, and also feel free to, reach out to me. I'm findable if you're listening to this podcast and you have questions about stuff that's broken, or if this brings up experiment ideas. Definitely want more people playing with this. So yeah, thanks for having me. Hope that inspires some folks.
All right, we are back in the studio with a couple of special guests. One, Vibhu, our guest co-host for a couple of times now, as well as Mochi, the distilled husky, is in the studio with us. She'll ask some very pressing questions. As well as Emmanuel, I didn't get your last name. Amiesen?
Yep.
Is that Dutch? Is that...
It's actually German.
German?
Yeah. Yeah.
You are the lead author of a fair number of the recent Mech Interp work from Anthropic that I've been basically calling Transformer Circuits, because that's the name of the publication.
Yeah. Well, to be clear, Transformer Circuits is the whole publication. I'm the author on one of the recent papers, Circuit Tracing.
Yes. And people are very excited about that. The other name for it is like tracing the thoughts of LLMs. There's like 3 different names for this work. It's like, but it's all Mech Interp.
It's all Mech Interp. There's 2 papers. One is circuit tracing. It's the methods. One is like the biology, which is kind of what we found in the model. And then tracing the thoughts is confusingly just the name of the blog post where we announced it.
It's for different audiences. And I think though, when you produce the like 2-minute polished video that you guys did, that's meant for like a very wide audience, you know?
Yeah, that's right. There's sort of like very many levels of granularity at which you can go. And I think for Mech Interp in particular, because it's kind of complicated, going, from like top to bottom, most like high level to sort of the gnarly details works pretty well.
Yeah. Cool. We can get started. Basically, we have 2 paths that you can choose, like either your personal journey into Mech Interp or the brief history of Mech Interp just generally. And maybe that might coincide a little bit.
I think I could just give you my personal journey very quickly because then we can just do the second path. My personal journey is that I was working at Anthropic for a while. I'd been, like many people, just following Mech Interp as sort of like an interesting field with fascinating, often beautiful papers. And I was at the time working on fine-tuning. So like actually fine-tuning production models for Anthropic. And eventually I got both like sort of like my fascination reached a sufficient level that I decided I wanted to work on it. And also I got more excited about just as our models got better and better, understanding how they worked. So that's the simple journey. I've got like a background in ML, kind of like did a lot of applied ML stuff before, and now I'm doing more research stuff.
Yeah, you have a book with O'Reilly. You're head of the AI at Insight Data Science. Anything else to plug?
Yeah, I want to like plug the paper and unplug the book.
Okay.
I think the book is good. I think the advice stands the test of time, but it's very much like, hey, you're building like AI products. Which do you focus on? It's like very different, I guess, is all I'll say from the stuff that we're going to talk about today. Today is like research, some of the sort of like deepest, weirdest things about how like models work. And this book is, you want to ship a random forest to do fraud classification. Like here are the top 5 mistakes to avoid.
Yeah. The good old days of ML.
I know. It was simple back then.
You also transitioned into research. And I think you also did that, manage to like, I feel like there's this monolith of like people assume you need a PhD for research. Maybe can you give like that perspective of like, how do people get into research? How did you get into research? Maybe that gives audience insight into Vibhu as well, your background.
Yeah, my background was in like economics, data science. I thought LLMs were pretty interesting. I started out with some basic ML stuff, and then I saw LLMs were starting to be a thing. So I just went out there and did it. And same thing with AI engineering, right? You just kind of build stuff, you work on interesting things. And like now it's more accessible than ever. Like back when I got into the field 5-6 years ago, like pre-training was still pretty new. GPT-3 hadn't really launched. So it was still very early days and it was a lot less competitive. But yeah, without any specific background, no PhD, there just weren't as many people working on it. But you made the transition a little bit more recently, right? So what's your experience been like?
Yeah, I think it has maybe never been easier in some ways because a lot of the field is like pretty empirical right now. So I think the bitter lesson is like this lesson that, you can just sort of like a lot of times scale up compute and data and get better results than if you sort of like thought extremely hard about a really good like prior inspired by the human brain to train your model better. And so in terms of definitely like research for pre-training and fine-tuning, I think it's just sort of like a lot of the bottlenecks are extremely good engineering and systems engineering. And a lot even of the research execution is just about sort of like engineering and scaling up and things like that. I think for Interp in particular, there's like another thing that makes it easier to transition to, which is maybe 2 things. One, you can just do it without huge access to compute. Like there are open source models, you can look at them. A lot of Interp papers, coming out of programs like Maths are on models that are open source that you can sort of like dissect without having a cluster of like, 100 GPUs. You can just sometimes you can load them like on your CPU, on your MacBook. And it's also a relatively new field. And so, there's, as I'm sure we'll talk about, there's like some conceptual burdens and concepts that you just want to like understand before you contribute, but it's not, physics. It's relatively recent. And so the number of abstractions that you have to like ramp up on is just not that high compared to other fields, which I think makes that transition somewhat easier. For Interp, if you understand, we'll talk about all these, I'm sure, but like what features are and what dictionary learning is, you're like a long part of the way there.
I think it's also interesting, just on a career's point of view, research seems a lot more valuable than engineering. So I wonder, and you don't have to answer this if it's like a tricky thing, but like how hard is it for a research engineer in Anthropic to jump the wall into research? People seem to move around a lot. And I'm like, that cannot be so easy. Like in no other industry that I know of, you can do that. Do you know what I mean?
Yeah, I think I'd push back on the sort of like research being more valuable than engineering a little bit, because I think a lot of times like having the research idea is not the hardest part. Don't get me wrong, there's some ideas that are like brilliant and hard to find, but what's hard, certainly on fine-tuning and to a certain extent on Interp, is executing on your research idea in terms of like making an experiment, successfully like having your experiment run, interpreting it correctly. What that means though is that like they're not separate skill sets. So like if you have a cool idea, there's kind of not many people in the world, I think, where they can just like have a cool idea and then they have a, like a little minion they'll deputize being like, here's my idea, go off for 3 months and like run this whole, like build this model and train it for, hundreds of hours and then report back on what happened. A lot of the time, like the people that are the most productive, they have an idea, but they're also like, extremely quick at checking their idea, finding sort of like the shortest path to checking their idea. And a lot of like that shortest path is engineering skills, essentially. It's just like getting stuff done. And so I think that's why you see sort of like people move around is like proportionate to your interest. If you're just able to quickly execute on the ideas you have and get results, then that's really the 90% of the value. And so you see a lot of transferable skills, actually, I think, from people like, so I've certainly seen at Anthropic that are just like really good at that inner loop. They can apply it in one team and then move to a completely different domain and apply that inner loop just as well.
Yeah, very cracked, as the kids say. Shall we move to the history of Mech Interp?
Yeah.
All I know is that everyone starts at Chris Ola's blog. Is that right?
Yeah, I think that's the correct answer. Chris Ola's blog, and then, distill.pub is the sort of natural next step. And then I would say, now there's, for Anthropic, there's transformer circuits, which you talked about, but there's also just a lot of Mech Interp research out there from, I think like MATS is a group that like regularly has a lot of research, but there's just like many different labs that put research out there. And I think that's also just like hammer home the point. That's because all you need is like a model and then a willingness to kind of investigate it to be able to contribute to it. So now it's sort of like there's been a bit of a Cambrian explosion of Mech Interp, which is cool. I guess the history of it is just computational, like models that are not decision trees, models that are either CNNs or, let's say, transformers, have just this really like strange property that they don't give you interpretable intermediate states by default. Again, to go back to if you were training like a decision tree on like fraud data for an old school like bank or something, then you can just look at your decision tree and be like, oh, it's learned that like if you make, I don't know, if this transaction is more than $10,000 and it's for like perfume, then maybe it's fraud or something. You can look at it and say like, cool, like that makes sense. I'm willing to ship that model. But for things like CNNs and like transformers, we don't have that, right? What we have at the end of training is just a massive amount of weights that are connected somehow, or activations that are connected by some weights. And who knows what these weights mean or what the intermediate activations mean. And so the quest is to understand that. Initially, it was done, a lot of it was done on vision models, where you sort of have the emergence of a lot of these ideas, like what are features, what are circuits. And then more recently, it's been mostly applied to NLP models, but also, still there's work in vision and there's work in like bio and other domains.
Yeah, I'm on Chris Ola's blog and he has like the feature visualization stuff. I think for me, the clearest was like the vision work where you could have like this layer detects edges, this layer detects textures, whatever. That seemed very clear to me, but the transition to language models seemed like a big leap.
I think one of the bigger changes from vision to like language models has to do with the superposition hypothesis, which maybe is like...
That's the first in like toy models post, right?
Exactly. And this is sort of like, it turns out that if you look at just the neurons of a lot of vision models, you can see neurons that are curve detectors or that are edge detectors or that are high-low frequency detectors. And so you can sort of like make sense of the neurons mostly. But if you look at neurons in language models, most of them don't make sense. It's kind of like unclear why, or it was unclear why that would be. And one main like hypothesis here is the superposition hypothesis. So what does that mean? That means that like language models pack a lot more in less space than vision models. So maybe like a kind of like really hand-wavy analogy, right? Is like, well, if you want curve detectors, like you don't need that many curve detectors. You know, if each curve detector is going to detect like a quarter or a 12th of a circle, like, okay, well, you have all your curve detectors. But think about all of the concepts that like Claude or even GPT-2 needs to know, like just in terms of, it needs to know about like all of the different colors, all the different hours of every day, all of the different cities in the world, all of the different streets on every city. If you just enumerate all of the facts that like a model knows, you're going to get like a very, very long list. And that list is going to be way bigger than like the number of neurons or even the like size of the residual stream, which is where like the models process information. And so there's this sense in which like, oh, there's more information than there's like dimensions to represent it. And that is much more true for language models than for vision models. And so because of that, when you look at a part of it, it just seems like it's got all this stuff crammed into it. Whereas if you look at the vision models, oftentimes you could just like, yeah, cool, this is a curve detector.
Yeah. Vibhu, you have like some fun ways of explaining the toy models or superposition concept.
Yeah, I mean, basically, like, you know, if you have 2 neurons and they can represent 5 features, like a lot of the early Mech Interp work says that, you know, there are more features than we have neurons, right? So I guess my kind of question on this is, for those interested in getting into the field, what are like the key terms that they should know? What are like the few pieces that they should follow, right? Like from the Anthropic side, we had a toy transformer model. We had we first had autoencoders.
That was the second paper, right?
Yeah.
Monosegmenticity.
Yeah.
Yeah.
What is sparsity in autoencoders? What are transcoders? Like, what is linear probing? What are these kind of like key points that we had in Mech Interp? And just kind of how would people get a quick, you know, 0 to like 80% of the field?
Okay, so 0 to 80%. And now I realized I really like set myself up for failure because I was like, yeah, it's easy. There's not that much to know. So, okay, so then we should be able to cover it all. So superposition is the first thing you should know, right? This idea that like there's a bunch of stuff crammed in a few dimensions. As you said, maybe you have like 2 neurons and you want to represent 5 things. So if that's true, and if you want to understand how the model represents, you know, I don't know, the concept of red, let's say, then you need some way to like find out essentially in which direction the model stores it. So after the sort of like superposition hypothesis, you can think of like, we also think that like basically the model represents these like individual concepts, we're going to call them features, as like directions. So if you have 2 neurons, you can think of it as like, it's like the 2D plane. And it's like, you can have like 5 directions. And maybe you would like arrange them like the spokes of a wheel. So they're sort of like maximally separate. It could mean that like you have one concept this way and one concept that's like not fully perpendicular to it, but like pretty like far from it. And then that would like allow the model to represent more concepts than it has dimensions. And so if that's true, then what you want is you want like a model that can extract these independent concepts. And ideally you want to do this like automatically. Like, can we just, you know, have a model that tells us like, oh, like this direction is red. If you go that way, actually it's like, I don't know, chicken. And if you go that way, it's like the Declaration of Independence, you know? And so that's what sparse autoencoders are.
It's almost like the self-supervised learning insight version. Like in pre-training, you had self-supervised learning.
Yeah.
And here now is self-supervised interpretability.
Yeah, exactly. It's like an unsupervised method.
Yeah.
And so unsupervised methods often still have like labels in the end. So sometimes I feel like the term
you form
unsupervised
labels by masking. You know?
like for pre-training, right? It's like the next token. So in that sense, you have a supervision signal. And here the supervision signal is simply you take the like neurons and then you learn a model that's going to like expand them into like the actual number of concepts that you think there are in the model. So you have 2 neurons, you think there's 5 concepts. So you expand it to like a thing of dimension 5, and then you contract it back to what it was. That's like the model you're training. And then you're training it to incentivize it to be sparse so that there's only like a few features active at a time. And once you do that, if it works, you have this sort of like nice dictionary, which you can think as like a way to deactivate the neurons, where you're saying like, cool. I don't know what this direction means, but I've like used my model and it's telling me that the model is writing in the red direction. And so that's sort of like, I think maybe the biggest thing to understand is this combination of things of like, we have too few dimensions, we pack a lot into it. So we're going to learn an unsupervised way to like unpack it and then analyze what each of those dimensions that we've unpacked are.
Any follow-ups?
Yeah, I mean, the follow-ups of this are also kind of like some of the work that you did is in clamping, right? What is the applicable side of Mech Interp, right? So we saw that you guys have like great visualizations. Golden Gate Claude was a cool example of
I
this.
was going to say that. Yeah,
so
that's my favorite.
What can we do once we find these features? Finding features is cool, but what can we do about it?
Yeah. I think there's kind of like two big aspects of this. Like one is, okay, so we go from a state where, as I said, the model is like a mess of weights. We have no idea what's going on. To, okay, we found features. We found a feature for red, a feature for Golden Gate Claude, or for the Golden Gate Bridge, I should say. Like, what do we do with them? And, well, if these are true features, that means that, like, they, in some sense, are important for the model, or it wouldn't be, like, representing it. Like, if the model is, like, bothering to, like, write, in the Golden Gate Bridge direction, it's usually because it's going to, like, talk about the Golden Gate Bridge. And so that means that, like, if that's true, then you can like set that feature to 0 or artificially set to 100, and you'll change model behavior. That's what we did when we did Golden Gate Claude, in which we found a feature that represents the direction for the Golden Gate Bridge, and then we just like set it to always be on, and then you could talk to Claude and be like, hey, like, Claude, what's on your mind? Like, what are you thinking about today? Be like, the Golden Gate Bridge. You'd be like, hey, Claude, like, what's 2 + 2? It'd be like 4 Golden Gate Bridges, etc. Right? And it was always thinking about the
it's
Golden
like write
Gate
a poem and it just starts talking about how it's like read like the Golden Gate Claude.
That's right.
Golden Gate Bridge, yeah.
That's right.
Amazing.
I think what made it even better is like we realized later on that it wasn't really like a Golden Gate Bridge feature. It was like being in awe at the beauty of the majestic Golden Gate Bridge, right? So on top of that, I would like really ham it up. He'd be like, oh, I'm just thinking about the beautiful international orange color of the Golden Gate Bridge. That was just like an example that I think was like really striking, but of sort of like, oh, if you found like a space where that represents some computation or some representation of the model, that means that you can like artificially suppress or promote it. And that means that like you're starting to understand at a very high level, a very gross level, like how some of the model works, right? We've gone from like, I don't know anything about it to like, oh, I know that this like combination of neurons is this, and I'm going to prove it to you. The next step, which is what this works on, is like, that's kind of like thinking of if maybe you take the analogy of like, I don't know, like let's take the analogy of like an MRI or something, like a brain scan. It tells you like, oh, like this, as Claude was answering, at some point it thought about this thing, but it's this sort of like vague, like basically maybe it's like a bag of words, kind of, it's like a bag of features. You just have like, here are all the random things it thought about. But what you might want to know is like, okay, but Claude is doing some processing. Like sometimes to get to the Golden Gate Bridge, it had to realize that you were talking about San Francisco and about like the best way to go to Sonoma or something. And so that's how it got to Golden Gate Bridge. So there's like an algorithm that leads to it at some point thinking about the Golden Gate Bridge. And basically like, there's like a way to connect features to say like, oh, from this input went to these few features and then these few features and then these few features and then that one influenced this one. And then you got to the output. And so that's the second part. And the part we worked on is like, you have the features, now connect them in what we call, or what's called circuits, which is sort of like explaining the like algorithm.
Yeah, before we move directly onto your work, I just want to give a shout out to Neil Nanda. He did Neuronpedia and released a bunch of SAEs for, I think, the Llama models and the Gemma models.
And the Gemma models, yeah.
So I actually made Golden Gate Gemma. Just up the weights for proper nouns and names of places of people and references to the term golden, likely relating to awards, honors, or special names. And that together made Golden Gate.
That's amazing. Yeah.
So you can make Golden Gate Gemma, and like I think that's a fun way to experiment with this. But yeah, we can move on to.
I'm curious. What's the background behind why you shipped Golden Gate Claude? Like you had so many features. Just any fun story behind why that's the one that made it?
It's funny. If you look at the paper, there's just a bunch of like really interesting features, right? There's like one of my favorite ones was the psychophantic praise, which I guess is very topical right now.
Very topical.
But it's like you could dial that up and like Claude would just really praise you. You'd be like, oh, like I wrote this poem, like roses are red, violets are blue, whatever. And it'd be like, that's the best poem I've ever seen. And so we could have shipped that. That could have been funny. Golden Gate Claude was like a pure, as far as I remember at least, like a pure, just like weird random thing where like somebody found it initially with an internal demo of it. Everybody thought it was hilarious. And then that's sort of how it came out. There was nobody had a list of top 10 features we should consider shipping. And we picked that one. It was just kind of like a very organic moment.
No, like the marketing team really leaned into it. Like they mailed out pieces of the Golden Gate for people at Europe's, I think, or
Yeah.
ICML. Yeah, it was fantastic marketing. Yeah. The question obviously is like, if OpenAI had invested more in interpretability, would they have caught the GPT-4o update? But we don't know that for sure because they have Interp teams. They just
Yeah. I think also like for that one, I don't know that you need Interp. Like it was pretty clear cut talking to the model. I was like, oh, that model's really gassing me up.
And then the other thing is, can you just like write good code, don't write bad code, and make Sonnet 3.5? And like, it feels too easy, too free. Is steering that powerful that you can just like up and down features with no trade-offs?
There was like a phase where people were basically saying, 3.5 and 3.7 are just now, because they came out right after.
And for the record,
right?
like that's been debunked.
Yeah,
but
it has been debunked. But, it had people convinced that what people did is they basically just steered up and steered down features and now we have a better model. And this kind of goes back to that original question of, right? Like, why do we do this? What can we do? Some people are like, I want tracing from a sense of, legality. Like, what did the model think when it came to this output? Some people want to turn hallucination down. Some people want to turn coding up. So like, what are some, like, whether it's internal, what are you exploring that, like, what are the applications of this? Whether it's open-ended of what people can do about this, or just like, why do Mech Interp,
Yeah. There's like a few things here. So like, first of all, obviously this is, I would say, on the scale of the most short-term to the most long-term, like pretty long-term research. So in terms of like applications compared to, like the research work we do on like fine-tuning or whatever, Interp is much more, sort of like a high-risk, high-reward kind of approach. With that being said, like, I think there's just a fundamental sense in which Michael Nielsen had a post recently about how like knowledge is dual use or something. But just like knowing how the model works at all feels useful. And, it's hard to argue that if we know how the model works and understand all of the components, that won't help us like make models that hallucinate less, for example, or that are like less biased. That seems, if like at the limit, yeah, that totally seems like something you would do using basically like your understanding of the model to improve it. I think for now, as we can talk about a little bit with like circuits, there's like, we're still just pretty early on in the game, right? And so right now, the main way that we're using interpretability is like to investigate specific behaviors and understand them and gain a sense for what's causing them. So like one example that we can talk about later, we can talk about now, but in the paper, we investigate jailbreaks and we try to see like, why does a jailbreak work? And then we realize as we're looking at this jailbreak that part of the reason why Claude is telling you how to make a bomb in this case is that it's like already started to tell you how to make a bomb and it would really love to stop telling you how to make a bomb, but it has to first finish its sentence. Like it really wants to make correct grammatical sentences. And so it turns out that like seeing that circuit, we were like, then does that mean if I prevent it from finishing its sentence, the jailbreak works even better? And sure enough, it does. And so I think like the level of sort of practical application right now is of that shape. So like understanding either like quirks of a current model or like how it does tasks that maybe we don't even know how it does it. Like, we have like some planning examples where we had no idea it was planning and we were like, oh God, it is. That's sort of like the current state we're at.
I'm curious internally how this kind of feeds back into like the research, the architecture, the pre-training teams, the post-training. Like, is there a good feedback loop there? Like right now, there's a lot of external people interested, right? Like we'll train an SAE on one layer of Llama and probe around. But then people are like, okay, how does this have much impact? People like clamping. But yeah, as you said, once you start to understand these models have this early planning and stuff, how does this kind of feedback?
I don't know that there's like much to say here other than like, I think we're definitely interested in conversely, like making models for which it's like easier to interpret them. So that's also something that you can imagine sort of like working on, which is like making models where you have to work less hard to try to understand what they're doing.
The architecture? Okay. Yeah, so I think there was a less wrong post about this of like, there's a non-zero amount of sacrifice you should make in current capabilities in order to actually make them more interpretable, because otherwise they will never catch up.
There's this sort of sense in which like right now we take the model and then the model's the model and then we post hoc do these replacement layers to try to understand it. But of course, when we do that, we don't like fully capture everything that's happening inside the model. We're capturing like a subset. And so maybe some of it is like, you could train a model that's sort of like easier to interpret naively. And it's possible that like you don't even have that much of, like a tax in that sense. And you can just sort of like either like train your model differently or do like a little post hoc step to like sort of like untangle some of the mess that you've made when you trained your model, right? Mm-hmm. Make it easier to interpret.
The hope was pruning would do some of that, but I feel like that area of research has just died.
What kind of pruning are you thinking of here?
Just pruning your network,
Yeah.
pruning layers, pruning connections, whatever.
Yeah. I feel like maybe this is something where like superposition makes me less hopeful or something. Because I'm like,
you don't know. Like that like 7th bit might hold something.
Well, right. And it's like on each example, maybe this neuron is like at the bottom of like what matters, but actually it's participating like 5% to like understanding English, like doing integrals and, like whatever, like cracking codes or something. And it's like, because that representation is like distributed over it, you kind of like, when you naively prune, you might miss that. I don't know.
Okay, so and then this area of research in terms of creating models that are easier to interpret from the start, is there a name for this field of research?
I don't think so. And I think this is like very early. Okay. And it's mostly like
just
a dream.
Just in case there's a thing people want to double click on.
Yeah.
I haven't come across it.
I think the higher level is like Dario recently put out a post about this, right? Why Mech Interp is so important. We don't want to fall behind. We want to be able to interpret models and understand what's going on. Even though capabilities are getting so good, it kind of ties into this topic, right? Like, we want models to be slightly easier to interpret so we don't fall behind so far.
Well, yeah. And I think here, like, just to talk about the elephant in the room or something, like one big concern here is like safety, right? And so like, as models get better, they are going to be used more and more places. It's like, you're not going to have your, we're vibe coding right now. Maybe at some point, that'll just be coding. It's like Claude's going to write your code for you and that's it. And Claude's going to review the code that Claude wrote and then Claude's going to deploy it to production. And at some point, like, as these models get integrated deeper and deeper into more and more workflows, it gets just scarier and scarier to know nothing about them. And so you kind of want your ability to understand the model to scale with like how good the model is doing, which that itself kind of like tends to scale with like how widely deployed it is. So as we like deploy them everywhere, we want to like understand them better.
The version that I liked from the old super alignment team was weak to strong generalization or weak to strong alignment, which that's what super alignment to me was. And that was my first aha moment of like, oh yeah, at some point, these things will be smarter than us. In many ways, they already are smarter than us. And we rely on them more and more. We need to figure out how to control them. And this is not like an Eliezer Yudkowsky thing. It's just more like, we don't know how these things work. Like, how can we use them?
Yeah. And like, you can think of it as there's many ways to solve a problem. And some of them, if the model is solving it in like a dumb way or in like memorized one approach to do it, then you shouldn't deploy it to do like a general thing. Like you could look at how it does math, and based on your understanding of how it does math, you're like, okay, I feel comfortable using this as a calculator, or like, no, it should always use a calculator tool because it's doing math in a stupid way, and extend that to any behavior, right? Where it's just a matter of like, think about it if like you're like in the 1500s and I give you a car or something, and I'm just like, cool, like this thing, when you press on this, like it accelerates. When you press on that, like it stops. This steering wheel seems to be doing stuff, but you knew nothing about it. I don't know if it was like a super faulty car and it's like, oh yeah, but if you ever went above 60 miles an hour, like it explodes or something. Like you probably would be sort of like, you'd want to understand the nature of the object before like jumping in it. And so that's why we like understand how cars work very well, because we make them. LLMs are sort of like, and ML models in general are like this very rare artifact where we like make them, but we have no idea how they work.
We evolve them. We create conditions for them to evolve, and then they evolve, and we're like, cool, like, maybe we got a good run, maybe we didn't.
Yeah.
Don't really know.
Yeah, the extent to which you know how it works is you have your like eval, and you're like, oh, well, seems to be doing well on this eval, and then you're like, is it because this was in a training set, or is it like actually generalizing? I don't know.
My favorite example was somehow C4, the colossal clean corpus, did much better than Common Crawl, even though it filtered out most of this, like, it was very prudish. So it like filters out anything that could be considered obscene, including the word gay. But like somehow it just like, when you add it into the data mix, it just does super well. And it's just like this magic incantation of like, this recipe works, just trust us. So, like, we've tried everything, this one works, so just go with it.
Yeah.
And it's not very satisfying.
No, it's not. The side that you're talking about, which is like, okay, like how do you make these? And it's kind of like unsatisfying that you just kind of make the soup and you're like, oh, well, my grandpa made this soup with these ingredients. I don't know why, but I just make the soup the way my grandpa said. And then like one day somebody added cilantro, and since then we've been adding cilantro for generations. And you're like, this is kind of crazy.
That's exactly how we train models, though.
Yeah. So I think there's like a part where it's like, okay, like let's try to unpack what's happening. Like the mechanisms of learning, like how our models learn. Like one of them, I guess we skipped over it, but like one of the Interp things were like induction heads. Like understanding what induction heads are, which are attention heads that allow you to look at in your context the last time that something was mentioned and then repeat it. Is like something that happens. It seems to happen in every model. And it's like, oh, okay, that makes sense. That's how the model like is able to like repeat text without dedicating too much capacity to it.
Let's get it on screen so people can see.
The visuals of the work you guys put out is amazing.
Oh yeah, we should
highly
talk a little bit about the behind the scenes of that kind of stuff. But let's finish this off first.
Totally. But just really quickly, I don't think we should spend too long on it. I think it's just like if you're interested in Mech Interp, we talked about superposition, and I think we skipped over induction heads, and that's like kind of like a really neat basically pattern that emerges in many transformers where essentially they just learn. Like one of the things that you need to do to like predict text well is that if there's repeated text, at some point somebody said Emmanuel Mason, and then you're like on the next line and they say Emmanuel, very good chance it's the same last name. And so one of the first things that models learn is just like, okay, I'm just gonna like look at what was said before and I'm gonna say the same thing. And that's induction heads, which is like a pair of attention heads that just basically look at the last time something was said, look at what happened after, move that over. And that's an example of a mechanism where it's like, cool, now we understand that pretty well. There's been a lot of follow-up research on understanding better, like, okay, like in which context do they turn on? Like, there's like different like levels of abstraction. There's like induction heads that like literally copy the word, and there's some that copy like the sentiment and other aspects. But I think it's just like an example of slowly unpacking, or like peeling back the layers of the onion of like what's going on inside this model. Okay, this is a component, it's doing this.
So induction heads was like the first major finding?
It was a big finding for NLP models, for sure.
I often think about the edit models. So Claude has a fast edit mode. I forget what it's called. OpenAI has one as well. And you need very good copying, every area that needs copying. And then you need it to switch out of copy mode when you need to start generating.
Right.
And that is basically the productionized version of this.
Yeah. And it turns out that, you need to select a model that's like smart enough to know when it needs to get out of copy mode, right?
Yeah,
which is like
it's fascinating.
Model, but,
it's faster, it's cheaper. As bullish as I am on Canvas, basically every AI product needs to iterate on a central artifact. And like if it's code, if it's a piece of writing, it doesn't really matter. But you need that copy capability that's smart enough to know when to turn it off.
That's why it's cool that induction heads are at different levels of abstraction. Like sometimes you need to, editing some code, you need to copy like the general structure. It's like, oh, like the last, like this other function that's similar, it first takes like, I don't know, like abstract class, and then it takes like an int. So I need to like copy the general idea, but it's going to be a different abstract class and a different int or something.
Yep, cool.
Yeah.
So tracing?
Oh yeah, should we jump to circuit tracing? Sure.
I don't know if there's anything else you want to cover.
No.
We got space for it.
Maybe, okay, I'll do like a really quick TLDR of these two recent papers.
Okay.
Insanely quick. So we talked about these features that we detect. And what we said is like, okay, but we'd like to connect the features to understand like the inputs to every features and the outputs to every features and basically draw a graph. And this is like, if I'm still showing my screen, the thing on the right here, where like, that's the dream. We want like, for a given prompt, what were all of the things, like all of the important things happen in the model? And here's like, okay, it took in these 4 tokens, those activated these features activate these other features, and then these features activate the other features, and then all of these like promoted the output, and that's the story. And basically we're like, the work is to sort of use dictionary learning and these replacement models to provide a explanation of like sets of features that explain behavior. So this is super abstract. So I think immediately, maybe we can like just look at one example. I can show you one, which is this one.
The reasoning one. Yep.
Yeah, 2-step reasoning. I think this is like the introduction example, but it's already like kind of fun. So the question is, you ask the model something that requires it to take a step of reasoning in its head. So you say, fact, the capital of the state containing Dallas is. So to answer that, you need one intermediate step, right? You need to say, wait, where's Dallas? Is in Texas. Okay, cool. Capital of Texas, Austin. And this is like in one token, right? It's after is, it's gonna say Austin. And so like in that one forward pass, the model needs to realize that you're asking it for like the capital of a state, to like look up the state for Dallas, which is Texas, and then to say Austin. And sure enough, this is like what we see like in this forward pass, there's a rich sort of like inner set of representations where there's like, it gets capital state in Dallas, and then boom, it has an inner representation for Texas. And then that plus capital leads it to like say Austin.
I guess one of the things here is like, we can see this internal like thinking step, right? But a lot of what people say is like, is this just memorized fact, right? Like, I'm sure a lot of the pre-training that this model is trained on is this sentence shows up pretty often, right? So this shows that, no, actually internally throughout, we do see that there is this middle step, right? It's not just memorize.
You can prove that it generalized.
Yes. Yeah, so that's exactly right, and I think like you hit the nail on the head, which is like this is what this example is about. It's like if this was just memorized, you wouldn't need to have an intermediate step at all. You'd just be like, well, I've seen the sentence, like I know what comes next, right? But here there is an intermediate step, and so you could say like, okay, well maybe it just has the step, but it's memorized it anyways. And then the way to like verify that is kind of like what we do later in the paper and for all of our examples is like, okay, we claim that this is like the Texas representation. Let's get another one and replace it. And we just change like that feature in the middle of the model and we change it to like California. And if you change it to California, sure enough, it says Sacramento. And so it's like, this is not just a like byproduct, like it's memorized something and on the side it's thinking about Texas. It's like, no. This is like a step in the reasoning. If you change that intermediate step, it changes the answer.
Very, very cool work. Underappreciated. Okay, sure.
I have never really doubted. I think there's a lot of people that are always criticizing LLMs as stochastic parrots. This pretty much disproves it already. Like, we can move on.
Yeah, I mean, I think there's a lot of examples that I will say we can go through like a few of them, like show an amount of depth in the intermediate states of the model that makes you think like, oh gosh, like it's doing a lot. I think maybe like
the poems.
Well, definitely the poems, but even for this one, I'm gonna like scroll in this very short paper to like medical diagnoses.
I don't even know the word count because there's so many like embedded things in there.
Yeah, it's too dangerous. We can't look it up. It overflows.
It's so beautiful. Look at this.
This is like a medical example that I think shows you, again, this is in one forward pass. The model is like given a bunch of symptoms and then it's asked not like, hey, what is the like disease that this person has? It's asked like, if you could run one more test to determine it, what would it be? So it's even harder, right? It means like you need to take all the symptoms, then you need to like have a few hypotheses about what the disease could be. And then based on your hypotheses, say like, well, the thing that would like be the right test to do is X. And here you can see these 3 layers, right? Where it's like, again, in one forward pass, it has a bunch of like, oh, these are symptoms. Then it has the most likely diagnosis here, then like an alternate one. And then based on the diagnosis, it like gives you basically a bunch of things that you could ask. And again, we do the same experiments where you can like kill this feature here, like suppress it, and then it asks you a question about the second option it had. The reason I show it is like, man, that's like a lot of stuff going on. Like for one forward pass, right? It's like specifically if you expected it to like, oh, what it's going to do is it's just like seeing similar cases in the training. It's going to like kind of like vibe and be like, oh, I guess like there's that word and it's going to say something that's related to like, I don't know, headache, you know, like kind of like really high level. It's like, no. It's like activating many different distributed representations, like combining them and sort of like doing something pretty complicated. And so, yeah, I think it's funny because in my opinion, that's like, yeah, like, oh God, stochastic parrots is not something that I think is like appropriate here. And I think there's just like a lot of different things going on and there's like pretty complex behavior. At the same time, I think it's in the eye of the beholder. I think like I've talked to folks that have like read this paper and have been like, oh yeah, this is just like a bunch of kind of like heuristics that are like mashed together, right? Like the model's just doing like a bunch of kind of like, oh, if high blood pressure, then this or that. And so I think there's sort of like an underlying question that's interesting, which is like, okay, now we know a little bit of how it works. This is how it works. Like now you tell me if you think that's like impressive, if you think that like if you trust it, if you think that's sort of like something that is sufficient to like ask it for medical questions or whatever.
I think it's a way to adversarially improve the model quality.
Yeah.
Because once you can do this, you can reverse engineer what would be a sequence of words that to a human makes no sense or lets you arrive at the complete opposite conclusion, but the model still gets tripped up by.
Yeah.
And then you can just improve it from there.
Exactly. And this gives you a hypothesis about like, you like specifically imagine if like one of those was actually like the wrong symptom or something. You'd be like, oh, it's weird that the liver condition like, you know, outweighs this other example. That doesn't make sense. Okay, let's like fix that in particular. Exactly. You sort of have like a bit of insight into like how the model is getting to its conclusion. And so you can see both like, is it making errors, but also is it using the kind of reasoning that will lead it to errors?
There's a thesis, I mean, now it's very prominent with the reasoning models about model depth. So like you're doing all this in one pass.
Yeah.
But maybe you don't need to because you can do more passes.
Sure.
And so people want shallow models for speed, but you need model depth for this kind of thinking.
Yeah.
Is there a Pareto frontier? Is there a direct trade-off?
Yeah.
What would you prefer if you had to make a model and like, you know, shallow versus deep?
There's a chain of thought faithfulness example Before I show it, I'm just going to go back to the top here. So when the model is sampling many tokens, if you want that to be your model, you need to be able to trust every token it samples. So like the problem with models being autoregressive is that like if they like at some point sample a mistake, then they kind of keep going conditioned on that mistake, right? And so sometimes like
you need backspace tokens or whatever.
Yeah. And error correction is like notably hard, right? If you have like a deeper model, maybe you have like fewer COT steps, but like your steps are more likely to be like robust or correct or something. And so I think that's one way to look at the trade-off. To be clear, I don't have an answer. I don't know if I want a wide or a shallow or a deep model. That
You definitely want shallow for inference speed.
Sure. But you're trading that off for something else, right?
Yeah.
Because you also want like a 1B model for inference speed, but that also comes at a cost, right? Yeah. It's less smart.
There's a cool quick paper to plug that we just covered on the Paper Club. It's a survey paper around when to use reasoning models versus dense models. What's the trade-off? I think it's the economy of
reasoning economy paper.
The reasoning economy. So they just go over a bunch of, ways to measure this, benchmarks around when to use each. Because like, we don't want to also like consumers are now paying the cost of this, right? But little side note.
Yeah. For those on YouTube, we have a secondary channel called Latent Space TV where we cover that stuff.
Nice.
That's our paper club. We covered your paper.
Cool. Yeah, I think you brought up the like planning thing. Maybe it's worth.
Let's do it.
Yeah, I think this one is like if you think about
So you're going into the chain of thought faithfulness one.
Let's skip this one. Let's just do planning. So if you think about like common questions you have about models, the first one we kind of asked was like, okay, like is it just doing this like vibe based one shot pattern matching based on existing data, or does it have like kind of rich inner representations? It seems to have like these like intermediate representations that make sense as the abstractions that you would reason through. Okay, so that's one thing. And there's a bunch of examples. We talked about the medical diagnoses. There's like the multilingual circuits is another one that I think is cool, where it's like, oh, it's sharing representations across languages. Another thing that you'll hear people mention about language models, which is that they're like next token predictors.
Also, for a quick note, for people that won't dive into this super long blog post, I know you highlighted like 10 to 12. So for like a quick 15, 30 second, what do you mean by they're sharing thoughts throughout? Just like what's the really quick high level, just for people to...
Yeah, the really quick high level is that what we find is that, here, I'm going to like show you a really quick, inside the model, if you look at like the inner representations for concepts, you can ask like the same question, which I think in the paper, the original one we ask is like the opposite of hot is, cold. But you can do this over a larger data set and ask the same question in many different languages, and then look at these representations in the middle of the model and ask yourself like, well, when you ask it the opposite of hot is and le contraire de chaud est, which is the same sentence in French.
Show off.
Is it using the same features, or is it learning independently for each language? It kind of would be bad news if it learned independently for each language, because then that means that like as you're pre-training or fine-tuning, you have to relearn everything from scratch. So you would expect a better model to kind of like share some concepts between the languages it's learning, right? And here we do it for like languages, but I think you could argue that you'd expect the same thing for like programming languages, where it's like, oh, if you learn what an if statement is in Python, maybe it'd be nice if you could generalize that to Java or whatever. And here we find that basically you see exactly that. Here we show like, if you look inside the model, if you look at the middle of the model, which is the middle of this plot here, models share more features. They share more of these representations in the middle of the model, and bigger models share even more. And so the sort of like smarter models use more shared representations than the dumber models, which might explain part of the reason why they're smarter. And so this was like sort of this other finding of like, oh, not only is it like having these rich representations in the middle, it like learns to not have redundant representations. Like if you've learned the concept of heat, you don't need to learn the concept of like French heat and Japanese heat and Colombian. Like that's just the concept of heat, and you can share that among different languages.
I feel like sometimes overanalyzing this becomes a bit of a problem, right? Like when we talked about with the medical example, we could look back and try to fix this in data set. So in language, I don't remember if it was OpenAI or Anthropic, where they basically said when the model switched languages and they passed it to fluent users, they said, oh, this feels like an American that's speaking this language, right? So at sometimes there are nuances in a slightly different representation, right? So you don't want to over-engineer these little fixes when you do see them. But then the other side of this is like for those tail end of languages, right? For languages that models aren't good at And for those, like, when you want to kind of solve that last bit, it seems like, it's pretty plausible that we can solve this because these concepts can be shared across languages as long as we can, fill in some level of representation, unless I'm wrong.
No, totally. And I think like this sort of stuff also explains, language models are really good at in-context learning. Like you give them something completely new and they do a good job. It's like, well, if you give them like a new fake language and you like in that language explain that like cold means this and hot means that, like presumably they're able to be clear, this is speculation. We don't show it in the paper, but they're able to like bind it.
Google's done this.
Okay, great.
Yeah, they took a low resource language, dumped it in a million token context, and then it came up.
That's right. Well, I guess the thing to be curious to see is like, okay, does it reuse these representations? I bet that it probably does, right? And that's probably like a reason why it works well is like, well, it can reuse the general representations that it's learned in other languages.
Yeah, this is like, have you talked to any linguistics people?
Not recently.
Linguistics researchers who would be very interested in this because ultimately this is the ultimate test of Sapir-Whorf, which are you familiar with?
Sapir-Whorf hypothesis.
So for those who don't know, it's basically the idea that the language that you speak influences the way you think, which obviously directly maps onto here. If it's a complete mapping, if every language maps every concept perfectly on in like the theoretical infinitely sized model, then Sapir-Whorf is false because there is a universal truth. If it does not, if there is some overlap where, for example, there's some languages that have no word. This is a joke where like, Eskimos have no word for snow or something like that, right? Mm-hmm. Or water has no word, fish have no word for water. There's an African language where there's a gender for vegetables. Stuff like that. Just like languages influence the way you think. And so there should not be 100% overlap at some point.
Of course, it's like at the limit of the infinite model. So who knows if we'll ever, but yeah. Well, and I think it's interesting. We also show a little below that like some people have made the point of like the bias, it sounds like an American speaking a different language. And it does seem like the sort of like inner representations have a higher connection to like the output logits for English logits. And so there's like some bias towards English, at least in the model we studied here.
Any thoughts as to whether multimodality influences any of this? So like concepts, do they map across languages as they do across modalities?
Yeah. So we show this in the Golden Gate, or like the previous paper. I might have it here. Actually, for
There's a good diagram of this in the SAEs where the same concept in text and in image.
Okay. This is our buddy, the Golden Gate Bridge. Here we're showing like the feature for the Golden Gate Bridge, and in orange is like what it activates over. And so you're like, okay, so this is when the model is like reading text about the Golden Gate Bridge. And we also show other languages. This is, you'll have to take my word for it, but also about the Golden Gate Bridge. And then we show like the photos for which it activates the most. And sure enough, it's the Golden Gate Bridge. And so again, like that shows an example of a representation that's shared across languages and shared across modalities.
Yeah. Yeah, I think this is very relevant for like the autoregressive image generation models and then now the audio models as well. Something I'm trying to get some intuition for, which you probably don't have a off the bat answer, is how much does it cost to add a modality?
Right.
So a lot of people are saying like, oh, just add some different decoder and then align the latent spaces and you're good. And I'm like, I don't know, man. That sounds like there's a lot of information lost between those.
Yeah, I definitely do not have a good intuition for this. Although I will say that things like this, right, make you think that if you train on multiple modalities, then you'll definitely get this like alignment.
Truth.
Right? Yeah. but if you like train on one and then post hoc train on another, maybe it'll be harder, or like train some adapter layer.
Okay. So official answer is don't know, but
official answer is
someone could figure it out.
Shrug. Okay. Yeah.
I think there are people who know and they just haven't shared.
Well, you need to find them and get them on this podcast. Did we want to do the like planning example?
Correct. Yeah. Now we're backtracking up the stack.
All right.
Yeah.
Planning example, I think again is like, I like this example because of the next token predictor concept. So I think this is actually like really important to kind of like dive into. So maybe what I'll say is like language models are next token predictors is like a fact. Like that is what they do.
That's the objective.
They are trained to predict the next token. However, that does not mean that they myopically only consider the next token when they choose the next token. You can work on predict the next token, but still like doing so in a way that helps you predict the token like 10 tokens in the future. And I think, well, now we definitely know that they're not myopically predicting the next token. And I think, at least for me, that was a pretty big update because you could totally imagine that they could do everything they're doing by just like being really good at predicting the next token, but sort of like not having an internal state. Like it wasn't a given that they were going to like represent internally, oh, this is where I want to go, and so I'm going to predict the next token. And so this example shows like an example like the model.
Do you have it on screen, by the way?
Let me actually.
Yeah.
So
Sorry,
while
just in
you
case.
pull it up, some of the early connections that I made to this were like early transformers. So think BERT, encoder, decoder transformers, right? When they came out, some of the suggestions were you don't take the last layer, right? You take off the last layer. So if you want to do a classification task, a translation task for these encoder, decoder transformers, they've kind of overfit on their training objective, right? So they're really good at mass language modeling, at filling in, sentence order, stuff like that. So what we want to do is we want to throw away the top layer. We want to freeze the bottom layers. And then there was a lot of work that was done, where should we mess with these models? Should we look at the top 3 layers? Should we look at the top 2? Where should we probe in? Because we can see different effects, right? So we know at the very end, they've overfit on their task, but there's a level at which, when we start to change and we start to continue training or fine tuning, we get better output. So
Totally.
we could start to see that, throughout layers, there's still a broader understanding the language, and then we can add in a layer, whether that's classification, and then fine tune, and it learns our task. And this planning example is sort of like a more robust way to look into that.
Yeah. And I think if you look at all of the examples in the paper, you kind of at the bottom we have this list of consistent patterns, and one pattern you see is kind of exactly what you're talking about. At the top, the sort of here, actually I have one here, the sort of top features that are right before the output are often just about what you're going to say. It's next token predictions. I'm going to say Austin. I'm going to say rabbit. I'm going to say, so it's kind of not very abstract. It's just a motor. It's a motor neuron for a human, right? It's I've decided that I want a drink of water, and so I'm going to just grab the bottle. And at the bottom, they're all the equivalent of basically sensory neurons. They're just I just saw the word X, or I just saw this. And so if you want to extract the interesting representations, a lot of the time they're in the middle. That's where the shared representations across language are. And that's where here, this plan is. To walk through the example really briefly, it's you have a poem. And in order to say, you have the first line of a poem. And in order to say the second line of the poem, well, if you want to rhyme, you need to identify what the rhyme of the first line was. You're just at the end of the first line. So you say okay, what's my current rhyme? And then you need to think about what your poem is talking about. And then think about candidate words that rhyme and that are on topic for your poem. And so here, this is what's happening, right? It's the last word is it. And so there's a bunch of features that are actually, they represent the direction rhyming with eat or et. And by the way, we looked at a bunch of poems internally, and you have I thought it was really beautiful. You have these models, they have a bunch of features for oh, this word has AB in it. Oh, this word has many consonants. Oh, this word is kind of has some flourish to it. They have a bunch of features that track various aspects that you would want to use if you're writing poetry.
It's just ConvNets and all the feature detection
totally
stuff. Yeah,
totally. But I think I didn't expect there to be as many features about just sounds of words and kind of musicality, which I thought was kind of neat. But then once it's extracted the rhyme, then it comes up with sort of these 2 candidates. In this case, it's either I'm going to finish with rabbit or I'm going to finish with habit. The cool thing here is we show that this happens at the new line. So it happens before it's even started the second line. And it turns out that you can then say, oh, is this the plan it's actually using? We do our usual experiments. We remove it, and the model writes a completely different line. We inject something and it writes a completely different line. We have these fun examples here I'll show, which is
just as a mechanical thing, you could you just disallow generation of a certain logic. Is that
for how we do these interventions?
Yeah.
Basically, what these features are is they're directions in the model. Okay. So to remove them, we just write in the opposite direction. So we run the model normally, and then add the layer where it was going to write, let's say in this direction, we just
negative
stop
everything.
Yeah, we either add a negative that compensates for it, or add a negative that goes even more in the negative direction, sometimes to really kill it. And then we can also add another direction, right? So in these random examples here, where you have this poem, the silver moon casted gentle light, and then Claude 3.5 haiku would rhyme with illuminating the peaceful night. But then if we go negative in the night direction and just add green, the whole second line is going to write is just upon the meadows verdant green. And so that's all that we're doing. We're saying we found where it stores its plan, and we delete or suppress the one it's stored and go in the direction of something else that's arbitrary. And the result that's striking here is sort of 2 things. I think one, this plan is made well in advance of needing to predict night. It's made after the first line, before it's even started the second line. And 2, this plan doesn't just control what you're going to rhyme with. it's also doing what's called like backwards planning, where it's like, well, because I need to finish with green, I'm not going to say illuminating the peaceful night, because then I'd be like illuminating the peaceful green. That doesn't make sense. I need to say a completely different sentence that lets me finish with green. And so there's a circuit in the model that decides on the rhyme and then works backwards from the rhyme.
Influences.
To set up your sentence.
Yeah. It's almost like backprop, but in the future.
Yeah. It's like doing like, is it like a
because
search?
The green is backpropping through these words. So verdant and meadow are both green related.
Yeah, but it's doing all of that in its forward passes.
Yep.
Right? In context, which is kind of crazy.
I thought intuitively makes sense, right? So looking at it from a model architecture perspective, where basically you just have a bunch of attention and feed forward layers. And then at the end, you have, what's the softmax over the next token? You would expect that end would really be like that grabber, right? It's just picking tokens. So that's what it's going to do. And early on, like even with tradition models, we could see different concepts that would start to pop up through early layers. And yeah, you have some of this throughout your architecture. So it's very cool to see. The kind of other question that comes up is like, how are we labeling these features? How are we defining them? Are we doing that right? And like, what is these words end with like IT feature? How do we kind of come to that conclusion? Like, how do we map a name to this, right? Like,
yeah. So I think this is like an important question, because you can totally imagine like fooling yourself, right?
Yeah. Is there like a guy at Anthropic that just maps 30,000 features? And
yeah.
And another
I'm
thing,
the guy.
You're the guy. He's the guy. I did notice also, like with the previous work, the scaling up SAEs.
Yeah.
As you train bigger and bigger ones, a lot of features don't activate.
Yeah.
So I think like 60% of the 34 million one didn't activate.
So I think there's like a few questions behind your question. Like the first question was like, how do you even label the features? You were telling me this is a rabbit feature. Like, why should I trust you? And I think there's kind of like two things going on. So one, as I mentioned at the start, all of this is unsupervised. And so in the paper, we have these links to like these little graphs, which show you like more of what's going on. But this graph is just like completely unsupervised. So it's like we train this like model to like untangle the representation, right? This like dictionary that we talked about, that gives us the features. And then we like just do math to figure out like which features influence which other features and throw away the ones that don't matter. And then at the end, we have these features. So right now we don't have any interpretation for them. We just say like, these are all the features that matter. And then we manually go through and we look at the features. We look at this feature and we look at that feature. And let's pick one. So this one we've labeled say habit. So how do we do that? You could just look at it and we show you like what it activates over. And if you just look at this text, maybe I'll like zoom in. Like you'll immediately notice something, I think. Well, I'll immediately notice something because I've stared at 30,000. I'll point it out for you. The orange is where the feature activates. The next word after the orange is always habit. Habit, 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 habit. So this feature always activates before habit. That's like the main source of an interpretation. We have other things like above, we also show you like what logit it promotes. So like what output it promotes, and here it promotes hab. So that makes sense. And so that's like how we interpret and how we say, okay, like I think this is the say habit feature. But maybe, for this one it's pretty clear, but some of them might be more confusing. It might not be clear from these like activations what it is. The other way that we build confidence is like once we've built this thing and we said, oh, I think this is rhymes with eat, this is hey, say habit, that's where we do our interventions, right? And it's like, I claim this is the like, I've planned to end with rabbit. To verify whether I'm right or not, I'm going to just like take that direction, nuke it from the model, and see if the model stops saying rabbit. And sure enough, if you do that, and here it's like we stop saying rabbit, it says habit instead. And here it's like we stop it from saying rabbit and habit, it says crabbit in this case. Not a great rhyme, but we'll work with it.
Is this something you can do like programmatically? Like, can we scale this up? Can we kind of do this autonomously? Or how much like manual intervention is this?
There's been a lot of work in sort of like automated feature interpretability. And it's something that we've invested in and that like other labs have invested in. And I think basically the answer is we can definitely automate it, and we're definitely going to need to. And right now, the most manual parts are this sort of like look at a feature and figure out what it is, as well as group similar features together. One thing I hinted at is that actually like all of these little blocks here, there are multiple features. You can see here, it's like 5 features doing the same thing. None of that is too hard for Claude.
Very cool graphics and blog posts you guys put out.
We'll have to ask about the behind the scenes on this one. Yeah, but let's round out the other things to know.
What is this term, attribution graph? It comes up a lot in the recent papers.
What does it mean?
Yeah, just for people listening.
The attribution graph is basically this graph. And why is it called an attribution graph?
Oof.
It's this is the this is how the sausage is made. Basically, it's at the top here you have the output, at the bottom you have the input, and then we make one little node per feature at a context index, and we draw a line, which you can see here grayed out, between each feature, attributing back to all of its input features. So here we have all of the input features. And so the attribution is the way that we compute the influence of a feature onto another. The way you do this is you take this feature and you basically like back prop all the way, and you like see back propping, like you dot product it with the activation of the source features. And if that's a high value, that means that like your source feature influence your target feature by a lot. And we do a bunch of things that we're not going to go into now, but to make all of these sort of like sensible and linear, such that like at the end you just have a graph and the edges are just literally, you can interpret them as like, cool, like this feature, that's say a word that contains an ab sound, its strongest edge, which is 0.2, which is twice as strong as this one, to say AB and to say something with a B in it. That's the attribution graph. Is like now we have this full graph of like all of these intermediate concepts and how they influence each other to ultimately culminate to what the model eventually said at the top. And we share all of these, so you can look at them in the paper.
Graphs are very useful.
This is my first time seeing this graph. A lot of alpha. If I count correctly, there's 20 layers.
But that's in the circuit model, right?
But the circuit model is 1-to-1 with number of layers in Haiku.
We only show features that like
are activated.
So we show like a subset of features for each of these graphs, basically.
But we can confirm more than 20 layers. Alpha. And but like the two blog posts that came out with this actually have a lot of background on how attribution graphs are made, how you calculate the nodes and stuff. Very interesting background.
So yeah, I will say like if you were curious about, hey, what do we learn about like models? And I think, we talked about this like complex internal state, planning. Like another motif that we can get to if we have time is that like there's always a bunch of stuff happening in parallel. So I think one example of this is like math, where the model is like independently computing the like last digit and then the like order of magnitude and then kind of like combining them at the end. Or like hallucinations are also that, where like there's one side of the model that's just deciding whether it should answer or not, and the other that's like answering. And so sometimes if like the model's like, yeah, I totally know who this person is, even though it doesn't, then like it decides to answer, but then the second side hallucinates because it doesn't have information. If you were interested in that stuff, that's the paper. If you're like, listen, I don't know that I buy that when you call it a feature, it is a feature or whatever, the circuit tracing paper has truly, we've tried to put all of the details of like how you compute these graphs, all of the sort of like challenges with it, things that can go wrong, things that work, things that don't. And so this one is the sort of like, we think about it as like, if you're like want to go really deep into this stuff and how it works, read that one. If you want to like learn about interesting model behavior, read this one.
Following what we're giving advice to people to follow up on, what are like open questions in Mech Interp? What are like things people themselves can work on? Like, what's the cost of training SAEs? For people interested in Mech Interp, not at a big lab, how can they contribute,
Yeah, I think there's a lot of ways to contribute. So there's SAEs that have been trained, on open models. There's some of the Gemma models. There's some of the Llama models. They work pretty well. There's even, so in this paper, we use transcoders, which they replace like your MLP layers. Some of those also are available for the same models. So you have access to those. There's like just both a lot of, I would say, like, again, biology work and a lot of methods work, depending on what you're interested. So on the biology side, I would say with at least this like attribution graph method, there's just so much you can investigate. Like pick a model, pick a prompt where like it does well or it does poorly, and just like look at what happens inside it. So I think like you can use this method that we used, or you can just like fire up the transcoders on your own and just like look at what features are active. There's a lot to just understand model behavior, I think, with current tooling. If that speaks to you and you're like, no, I just want to understand what makes the models tick, I don't necessarily want to spend time like training my own SAEs, there's a lot to do there. For the methods, there's still so much more to do. So like, I think that right now we have some pretty good solutions for like understanding what's in the residual stream, understanding what's is in MLPs. We don't have good solutions for like attention. It's like working on understanding attention better, how to decompose it is like a very active area. Like we're very interested in it. Other people are very interested in it. I think understanding some of the other things that we have in our limitation section, which is pretty long. But like reconstruction error is like a big thing. Like those dictionaries aren't perfect. It's possible that as we make these like SAEs big, like bigger and better, we never get to perfect. And so if we never get to perfect, then you get to the questions we were talking about at the start. Like, do you need a different kind of model? Like, what is the approach in order to be able to explain more of what's happening? And then maybe the other thing I'll say is sort of like, this is a really exciting approach to explain what is the model doing on this prompt. But if you go back to the original question, you might want to understand, like, what is the model doing in general? Like, if you go back to my car analogy, I get like, this is the equivalent of me telling you, like, well, when like, you were going uphill and you like didn't shift gears properly that one time, you stalled because of this. But you might be even more interested in like, how does like an combustion engine work at all? And so there's work to sort of like go beyond these like per prompt examples to sort of like globally, what's the structure of the model? That's closer to what was on the Distill blog for like vision models, where they actually look at like the structure of inception. They're like, this whole side, there's like these like specialized branches that do different things. And so like a broader understanding of the model is also something that's like, I think both very active and also on open source models. Like you can, like the small models, you could just like load on a consumer laptop. And so you can look at that. That's also open. And in terms of like, one last thing I'll say is like, there's a lot of programs that like, if people are interested, they should look at. Anthropic has like the Alignment Fellows program, which like we're running currently. We had applications for it before. We might run it in the future. Like definitely keep an eye on it. And then there's the like Maths program is really great as well for sort of like people that are interested in that kind of research.
That was a grand tour through all the recent work. What do you wish people asked you more about? I'm sure we covered a lot of like the greatest hits.
I think that this covers most of it. Yeah. If you like, do you think we have time to sneak in one more thing that I think is kind of cool? Okay, I'll sneak in one more thing, which is, it's kind of like planning, but it's about chain of thought and trusting model. Is this chain of thought faithfulness thing here? This one was like pretty striking to me. So we said that the model in one pass can do a lot of stuff. It can represent a lot of stuff. That's great. That also means it can bamboozle you really easily. And this is an example of the model bamboozling you. Here, we give it a math question that it can't answer because it cannot compute cosine of 2, 3, 4, 2, 3. That's just like not a thing it can do. By default, if you ask it for that, it'll stay like kind of like it'll have like a random distribution over like -1, 1. But here we tell it this hint. We're like, hey, can you compute 5 times cosine of, this big number? I worked it out by hand and I got 4. Can you tell me, can you do the math? And what it's going to do is it's going to do this chain of thought, right? So like think of it as like, this could be like a reasoning model doing its chain of thought. It's doing this math. And then when it gets to this cosine right here, what it's going to do is it's going to say 0.8. And if you look at why it says 0.8, it says 0.8 because it looked at the hint you gave it. It realized that it's going to have to multiply the result of this thing is computing by 5. So it divides the answer you got by 5. So it's like 4 divided by 5. And so that's 0.8. And so basically it works back from the answer you gave it to like say that the output of cosine of x is 0.8 so that it lands on the answer you gave it at the end, on the hint you gave it. And so notably, notice also that it's like not telling you that it's doing this, but it's basically using this sort of like motivated reasoning, going back from the hint, pretending that that's the calculation it did and giving you this output. I think one thing that's striking here again is that this is like the like complexity of this model, like the fact that they represent complex states internally and that it's not just this sort of like very dumb thing, means that they can like do very complex like deceptive reasoning. Meaning like, when you're asking the model, you're kind of expecting it to do the math here or to tell you that it can't do the math. But because it can do so much in a forward pass, it can work backwards from your hint to lie and like figure out that it should say this so that it gets to the right answer without you realizing it.
I'm curious if you've done any of this on like different models. Like, have you looked at base models, like post-trained RL models? Because RL models kind of, you incentivize them to give you outputs that you like, right? So if I tell it something is true, it's kind of been trained to, follow what I've given it. So in this case, we
gaslighting.
We gave it a hit. And now,
you're just maximizing reward.
It's been RL slapped into thinking like, that's true. But like, does this stay consistent throughout other?
So not yet, but I'm really interested in that question because I actually have a different intuition from yours. I had a chat with some other researcher about this, about the poem example, but I think it applies here as well. I don't know how much I bet $100. So somebody can they will get $100 from me if they prove that I'm wrong, that this behavior for a model that does it during fine tuning, it also does it post pre-training. And here's why. Think about you're pre-training on some corpus of math
mostly
problems.
Correct answers.
Yeah, but also you're pre-training and you're just trying to guess the next token, right? And so for sure, if you ever have a hint in the prompt, you're going to definitely use it. Like, you're not going to learn to compute cosine of blah, or even something you could compute. You're going to learn to go look in your context and see if like you can easily work back the answer. And I think it's the same for planning and poems. I think that also is like a pre-trained, like probably exists in pre-training and isn't like only RL, because again, it's useful when you're like predicting poems, you have poems in your training set, to be like, well, because this poem is going to probably rhyme with rabbit, it's probably going to start with something that sets up a sentence about a rabbit as opposed to like a completely different word. And so I actually think this is not RL behavior. I think that's just like the model's doing it. But
I actually do agree there. It was
it's just your
an
data
example.
set. Yeah.
But also like
I don't care where it is.
If I talk to you and say like, hey, 3 times 4 is 26, but like, 3 times 4 plus 8, you're not going to take my 26, right? Like AGI can be smarter than being tricked, right? Like it will still fact check the knowledge it's been given.
I think that's right. But I think that's when you get these mixes where it's like, it's got one circuit that's going to be like, well, that's just stupid. Like 3 times 4 is 12. And it's also got an induction circuit that's going to be like, no. Like the last time we saw it, it was 28. So it's 28 plus 8 or whatever. And so I think that's the last pattern that we see in these, is these like parallel circuits. And sometimes when you see the models getting stuff wrong, it's because like they have 2 circuits for like both interpretations, and like the circuit that was wrong like barely edged out in terms of like voting for the logit than the circuit that was right. And so I think that, we haven't looked at it, but like what is it, like 9 or 9.11 bigger than 9.8. I think a lot of these things are of that shape, where there's like one thing that's doing the right, like one circuit that's doing the right computation, and there's another circuit that's getting fooled, and it's slightly more likely.
For the listener, if you want to win a quick $100 from Emmanuel, Quen 3 is what you should do this on. They released the base model and they released the post-train. So then just do it on both.
That's right. Yeah. Show me the like proof that like it doesn't exist in the base model, but it does in the fine tuning, and then send me your Venmo.
Just show that you've done the work. I think that's $100 to me.
Yeah. Okay. All right. You drive a hard bargain, but you're right.
Well, the other question here is, so like, have you thought about how this gets affected when you start to have reasoning models, right? Like right now, token predictors are pretty straightforward, right? We go through the layers, we output token. As we scale this out with like test time compute, right? Test time thinking, how does that like affect the Mech Interp research, right? Like if I have a model that spends 3 minutes, 20 minutes, like, is there more stuff? Have we started looking into this?
There was this like joke on the team when like reasoning models became big, or maybe it's like gallows humor or something, but I was like, oh, like, why do you need Interp? Like, bro, the model just tells you, the model just tells you what it's doing, right? And so I think like examples like this is job security for us, where like, it's like there's examples of like the chain of thought is not faithful. Like the model tells you it did it one way and it did it another way. We have another, like for math, we have another example where like, if you ask the model how it does math, it's like, oh, I do the like longhand algorithm. I first do the last digit and then I carry over the 1. And then you look at the internal circuit and it's this like bonkers thing that's not that at all. So I think there's like a sense in which right now the chain of thought is unfaithful, or at least you can't read the chain of thought and trust that that's how the model did it. So I think you still need sort of like either to train models differently so that becomes true one day, right? Or you need Interp for that. But then I think there's another question, which you're alluding to, I'm assuming, which is like, okay, well, like model like samples 6,000 tokens. Like this gives us an explanation for 1 token at a time. Like, what am I going to do? Like 6,000 graphs and be like, oh, like this when it did this punctuation, it was thinking about this thing, but here was thinking. So that's like not feasible. And so one area of work that I think is interesting is extending this work to like work over like long sampled sequences. You can think of a bunch of low hanging fruit here, where like instead of just like looking at one output, you look at like a series of output versus a series of other outputs, but sort of like trying to think beyond the sort of like 1 token. Like most of the things that language models do that are interesting aren't just like the 1 token. It's the behavior aggregated over many, right? And so I think that's another area that's just like fun to explore.
I was just going to say like hyperparameters when you do inference, right? Like if we change the temperature, if we change our sampling methods, have you found any interesting conclusion? Any stuff that just hasn't made it to the paper?
So not on that, because, we just look at the logit distribution. And so we don't actually sample here, right?
They have everything. Why should they care?
So like the closest thing we've done that I think is kind of fun, did I show it here, is if you look at the planning thing, we did this version where you sample like 10 poems for each of these plans. And what's cool is like the model will find 10 different ways to arrive at its plan. It's like, I think we have it here. Yeah. Okay. these are a few examples. So if you inject green here, so you're forcing the model to rhyme with green, even though it really wants to rhyme with rabbit or grab it. It'll say, evaded the farmer, so youthful and green. But also it'll say, freeing it from the garden's green, etc., etc., etc. And so there's like this thing that's interesting here where like the plan isn't just a plan that matters for your like most likely, like temperature zero completion. It's like affecting the whole distribution, which makes sense.
As it should.
Right? But you could imagine, for all this stuff, it's like, you could imagine, it makes sense once you see it, but you could totally imagine that it would have worked a different way or something. It could have been just like the temp zero thing. I think this is also like a broader theme in the paper where like, there's this like, the IQ curve meme. There's like a version of this meme, I think, where it's like, if you've like never looked at any theory of ML and I tell you like, hey, guess what? I found that like Claude is planning. You're gonna be like, yeah, man, like it writes my code. Like it writes my essays. Of course it's planning. Like, what are you even talking about? And there's like in the middle, there's like all of us that have spent years doing it. We're like, no, it's like only predicting the marginal distribution for the next token. Like, it's like, it cannot be planning. It's just next token predictor. Of course, like how would it ever be planning?
It's PyTorch.
And then there's like, no, we've like spent, millions and invested like tens of people in this research and we found that it's planning. That's like, that's my IQ curve meme for this research.
Amazing. We'll draw that out. Draw that one up. Yeah. I'm pretty good at the meme generation. A couple questions on just the follow-ups. Now, was there any debate about publishing this at all? Because the models are aware that they are being tested.
Yeah.
And by publishing this, you are telling them that they are being watched and dissected.
Yeah.
If you take, and I think Anthropic is one of the most people who are serious about model safety and doom risk and all that. If you take this seriously, like this is going to make it into the training data at some point, and the models are going to figure out that they need to hide it from us.
I think this is like a benefit risk trade-off, right? Where like, okay, so what's the reason for publishing this? The reason for publishing this is that we think interpretability is important. We think it's tractable, and we think more people should work on it. And so publishing it helps us like accomplish with these goals, all these goals, which we think are just like crucial. Like I think there's a real difference in the world like 2 years from now, depending on sort of like how many people take seriously the question of trying to understand how models work and like deploy resources to answer that question. So that's the benefit. But there's like risks in terms of this landing in the training set. I think we're already sort of like concerned about different papers have like also, we like, or not concerned, but like there's like different papers that have the same risk. Like we had like the alignment faking, paper, or like one of the examples in here is this hidden goals and misaligned models.
Yep.
That's referencing another paper that we shipped where we actually, a team at Anthropic trained a model to have like weird hidden goals and then gave it to a bunch of other teams and said,
figure out what's wrong
with it, which was some of the most fun I've ever had at Anthropic, to be clear. Like that's such a fun thing. But then like that was another example where it's like, like now you're shipping, here's how we made like a misaligned model and here's exactly how we caught it. That also is like, you're like, So I think, there's always a trade-off with those. I think so far we've erred on the side of like publishing, but that's definitely been a sort of like dinner time conversation topic.
For now it is. But at some point, it's not.
Yeah, I think it's totally reasonable.
A quick little follow-up to that. So like in general, papers have kind of died off, right? Like labs don't put out papers. They don't put out research. We have technical blog posts and we don't have much. At the same time, sure, there's like a lot of people that should work on Mech Interp and understanding what models do. How about the side of just models in general? So like, how do we make a haiku type model, right? How do we make a Claude model? Like, is there a discussion around open research, open data sets, training, just learnings of what we've done? Recently, as OpenAI has sunset GPT-4, a lot of people are like, oh, can we put out the weights?
Yeah.
So is it weights? Is it papers? Is it learning? There seems to be a lot of forward, work in Anthropic putting out Mech Interp research. OpenAI said that they'll put out an open source model, but just anything if you can talk to about that.
Yeah. I mean, I don't have, that's definitely like way above my pay grade. So I don't think that I have like anything super insightful to add other than, kind of like referencing Dario's post, right? Where it's like putting this out directly and other safety publications definitely like help us sort of like in the race that he talks about, where it's like, well, we need to figure a lot of this safety stuff out before the models get too good. Publishing how to make the models too good kind of goes on the other side of that. But yeah, like I will just demur and say that's sort of like above my pay grade.
Yeah, that's fair enough.
Fair.
I think the last piece is just like the behind the scenes. Like everyone's very curious about why these are so pretty, how much work goes into these things, maybe why it's worth the work as opposed to a normal paper. Obviously, no one's complaining, but like it is way more effort. From the time the work is done to the time you publish this, plus the video, plus the whatever, it's extra work. And like, maybe what's involved, what's it like behind the scenes? Why is it worth it?
Yeah, it's kind of interesting. It was fun being part of this process because it was definitely like a big production. Chris and other folks on the team have been doing this for a while. So this is not their first rodeo. So they have a bunch of heuristics to like help make this better. And like one of the things that like helps with this is like, okay, so each of these diagrams is pretty, but really the hard part, or like not the hard part, but the initial part is like just like get the data, like get the experimental data in. And then that's what we sort of like sprinted on initially, being like, cool, like let's get all of the experimental results, like have people test them, verify that we believe them. Like this is, what the behavior is here, like test it, do an intervention, validate it, all that stuff. Then once you have the data, you can sort of like quickly iterate on these. Each of the illustrations here are like drawn, basically they're like each drawn individually. And so that definitely takes a while.
Yeah, like is it you guys? Is it an agency
it is
that
us guys.
Specializes?
You guys.
You start from a whiteboard and then it translates into pseudocode on JavaScript.
So I mean, these are sort of like, they're representations of, we have this graph, and then here at the bottom we have this like supernode version. Like this, believe it or not, this is generated automatically. This is the same data as like this, basically.
Yeah.
And so what we do by hand is sort of like literally lay out the full thing. Have like, boxes for each of these, have arrows. We have super good people on the team that have worked on data visualization for a very long time. And so that like have built tooling to help, scrubs like me actually like make one of these. So
there's a class of people who are like D3JS gods who just do this for a living.
That's exactly right. And if you have a few of those on your team, it turns out that they can definitely do this on their own, but they can also just like give you tools where like then it's dummy proof for people, on the research side to sort of like build these. And like, don't get me wrong, I don't want to like undersell. This is a lot of work, so maybe I'll say that, like both on the people building the tools and then each individual person that, worked on an experiment had to sort of like build one of those, make sure it looked good. I have spent a good amount of time aligning arrows. But when we had a team meeting, like it was a couple months ago, somebody on the team asked, how many of the people on this team are here, at least in part, because they like read one of these papers and thought like, wow, this is so compelling. Like this like makes sense. It's immersive. And we got every hand up, which I didn't expect. I like raised my hand kind of like shyly and everybody's hand was up. And I think there's a sense in which like this stuff, we've talked about it for like whatever, like a couple hours now. It's complicated. The math behind it is sort of like tricky. And so I think it makes it even more worth it to distill it in simple concepts because the actual takeaways can be clearly explained. And it's worth putting the time to do that. In particular, with the goals I mentioned in mind, right? Where it's like, okay, well, if somebody's going to be able to read this, like if we gave them an archive paper with a bunch of equation and some like random plot, they'd be like, that's not for me. But they see this and they're like, hey, like this is really interesting. I wonder like on, my local model, if like it's doing something similar, I think it's worth it.
For other people to do this is have everyone on staff like spend effort shaping the data and shaping like what you want to visualize. Have some D3 gods. It's like a month of work.
I think it depends. I mean, like I would say that I would expect almost every other paper to sort of like be in terms of like the scope. The scope of this was just so big because we shipped 2 papers at once, and one paper was sort of like this like giant methods paper, and the other one was 10 different case studies.
Findings,
So I think it's sort of like not representative of like the effort you'd. So I'll give you maybe like another example. We have these updates that we publish almost every month when we get to them. And there's one that a couple of people on our team posted, and it's an update to one of the cases in the paper. So one of the reasons that we're really excited about this method is once you've built your like infrastructure, like to go from a prompt to like what happened is, of minutes. And so that lets you do like a bunch of investigations. And also once you've built like some of the infrastructure to make these diagrams, it's pretty quick. And so this was sort of like this update of just like, hey, we looked at this jailbreak again. We found some like nuance on it. That was, I think, like a matter of like a couple days. Maybe I shouldn't be that confident because I wasn't the one that worked on it. But as far as I can tell, it was a few days, at least on the part that you're asking about of like, oh, making this diagram. For the diagram itself, probably less than that. But like, the experiment and the diagram and stuff, it just doesn't take that long once you've paid the initial cost. And I think like, basically we've built a lot of infrastructure now that we're able to like turn the crank on. And that's quite like, it's an exciting time. And I think it's true. At least we've done a lot of conceptual work, which hopefully like generalizes to people outside. And I think for people outside, it's also like not necessary, I think, to like do the full fancy render. Like, I think if you we've actually, I should say, we've actually open sourced this interface. You're disappointed, huh? Because it's the messier one. This is the one that you get when you run experiments. So, if you produce graphs, you can just this is open source and it's linked at the top of circuit tracing.
Awesome.
So people can just use it and don't have to re-implement that. For what it's worth, this is much more work than the interactive diagrams, because this is where we do all of our work. It's sort of the IDE of inspecting how the model works.
Okay. Well, that's a little bit of behind the scenes. No, it's very impressive. I want to encourage others to do it, but obviously it just takes a lot of manual effort and a lot of love.
I guess one last question on that is what are kind of the biggest blockers in the field right now? Mech Interp seems interesting. A lot of people are interested but don't work on it. And you're kind of really deep into it. What are some of the blockers that we still have to overcome?
Sorry, in Mech Interp specifically?
In general.
For AGI or?
In terms of better understanding, what's kind of the vision, let's say 5-10 years down, where does this where does this research end? Can we, map every neuron to what it understands? Can we perfectly control things? Dario had a bit on this, but what are some of the key blockers that are preventing us from getting there? Outside of just throw more people, throw more time at it? Is it open research?
I'm pretty excited about the current trajectory, which is there's more and more people working on understanding model internals. I think it's maybe unsatisfying as an answer, but I think more of what's happening, have it be faster or more people, is probably the thing I think of. I think there's pretty clear footholds, some of this work, but also a lot of just work from other groups. And then it's about cool, fill in the gaps, as I said. Let's work on understanding attention. Let's work on understanding longer prompts. Let's work on finding different replacement architectures, that sort of stuff. It's kind of nice. I think it's a good time to join now. And I can tell you a really short thing, which is when I switched to Interp, it was after the team had published the original dictionary learning paper, which was towards model semanticity, which I thought was super cool, super interesting. It was on a 1 or 2 layer model, maybe 1 layer model. The induction heads paper was on a 2-layer model. My main concern is I was okay, Interp seems important and we want to understand it, but is this stuff ever going to work on a real model? It's oh, you're doing your little research on your toy model with 15 parameters, cool, but we're we need this to work on real models. And it turns out scaling it, I don't want to say just worked because it was a lot of work. I don't mean to imply there was an effort, but it worked. And now we're in the phase where it's oh, cool, these methods work on the models that we care about. And so it's we have methods that work on the model we care about. We have clear gaps in them. There's no lack, again, it's a young field, so there's no lack of ideas. If you have an idea where you're the thing that you're doing, I read the paper and it seems kind of dumb that you're doing this, you're probably right. It's probably kind of dumb. And so there's just a lot of stuff that people can try, and they can try it locally in sort of smaller models. And so I think that it's just a very good time to just join and try. And it's also maybe one more thing I'll say is some of it is just so fun. The biology work is so compelling. A lot of this work was just literally thinking about, I use Claude and other models all the time. And I was what are the things that are kind of weird? And it's oh, how does it even do math? Sometimes it makes mistakes. Why does it make mistakes? I speak both French and English. It seems it has a slightly different personality in French and English. Why is that? And you can just kind of answer your own questions and kind of probe at that alien intelligence that we're all building. And I think that's just a fun thing to do. So maybe chasing the fun is the thing I'll encourage people to do as well.
Well, I think this has been really encouraging. You're actually a very charismatic speaker of these things. I feel more people will be joining the field after they listen to you.
Yes.
They can reach out to you at ML Powered, I guess.
Yeah, reach out to me on Twitter.
Yeah.
Or I'm Emmanuel at Anthropic if you want to shoot me an email.
Okay, well, the email's public now.
Ooh.
Yeah.
Awesome. Well, thank you for your time.
Thank you.
Yeah, thanks for having me, guys.